Hi, it's time for the class. And good morning, Brian, Yuzhen, Idris, Yao Yao. All right, great. Well, in terms of announcement, there's nothing more except maybe that Polly was too ambitious planning the lectures this week. We were saying that there'll be 3 quizzes doing this week, but you know what? Based on the progress, there'll be only 2 quizzes doing end of this week. Okay. But hey, guys, yeah, at the beginning of the semester, it is better to take a slower pace and make sure that you guys get the foundations built. Okay, so make sure that you understand what is internet first. Okay, and define the basic terms. Then the rest of the semester will get easier. Okay, so we might start slow, okay, at the beginning, but we'll gradually pick up the pace. Okay, today you might hear some of Polly's videos. We're running a faster pace. Okay, let me know how you feel when I play the video, like 10-20% faster. Okay, all right. So Rick, Tingjun, Kaixiang. I think Kaixiang is also Kevin. Okay, and also by the way, at the beginning of the semester, I might mix you guys up. All right, so sorry about that, but you know what, Polly will get better. Okay, Polly will definitely get better. Okay, Cheng Yao, morning, and I think Dolly is Doris. Okay, and Jiayi, you are Charlie. I mixed you up with Ethan earlier this morning. All right, and hi Davis. Great. Now let's go on and start with the first set of videos today, because last week we just finished comparing circuit switching and packet switching. So these are 2 general ideas of building a network such that it will go either smooth or promote sharing. Okay. Now, given that the internet is built based on PS, so let's talk more about PS. And the first video is I mentioned already. How come, right? We break the data and send in smaller packets. Why do we want to do that? Let's figure it out in this video. The next few slides, they are still somewhat important, okay, but not strictly talking about packet switching, circuit switching, and the comparison. So these slides are to answer a couple important questions. We said that packet switching, what it does is to divide data stream into small packets. But why not large packages? Right? We didn't really justify that. We kind of like that L divided by R. The time it takes to send one packet is small because this is small. And in case the link is really fast, then this is small. But if this is a little bit larger, well, not so bad either, isn't it? Well, think again. And this is the example that I try to use to set up the stage. And it's just a slightly extended version of the previous example where we have 2 hops only, just one router between the source and destination. The packet size 7.5 megabits and the link rate 1.5 megabits per second. And you see that L divided by R is 5 seconds. And because there are 3 hops, so this time store 5 seconds, 4, store 5 seconds, 4, and 5 more seconds to store. Altogether, 15 seconds to send this packet L. Now, 7.5 megabits, large, right? Sending a large package like this over this 3-hop network, 15 seconds. Let's try dividing this large message into smaller packets and see how it will work. 7.5 megabits, let's divide them into 5,000 packets. This way, each packet is only this big, 1.5K. Link rate is still what? 1.5 megabits. So to send a small packet like this, it takes only 1 millisecond. Now, look at this. This is the same network, 3 hops. Each packet is now very small. And to send one packet, the first router will take 1 millisecond to receive it and then send it out. So 1 millisecond, 2 milliseconds, and only 3 milliseconds until the destination receive the first packet. And you know what? These links can work in parallel, right? Because router 1 here can be passing packet 1 while the source start passing packet 2. You are trying to do also streamlining here, except that the unit of streamlining is a small packet. You see, why packet switching suggests small packets? Because it's trying to maintain the benefit of doing circuit switching. Unfortunately, we could not be streamlining bits, okay? But let's keep the packet small. Then we get to keep some of these nice properties in a circuit switch network. And having these links that can work independently is nice. We can pipeline or streamline the sending of the packets over the network. So each link works in parallel. And the overall delay in the end is what? 5002 milliseconds, only 5.002 seconds. If you recall earlier, if we send 5,000 small packets altogether, 7.5 megabits, each hop 5 seconds, and 3 hops 15 seconds. How much time are we saving? Big time, isn't it? This is why in packet switching, people always talk about cutting data into small packets. All right. Now you might be thinking, why we need to do store and forward in a packet switch network if we don't have to, right? Then we just send 1 bit per packet. Then it's just like circuit switching, isn't it? Well, in this next video, you'll see why. Okay. It's a little bit long, it's 7 minutes, so try to be a little bit more patient. And why do we need to store packets first before forwarding it, right? This is one of the reasons that we still need to form packets. Why we cannot just streamline the bits. The reason has something to do with how the routers is working. So inside the router, there are 2 key functionalities, and there are 2 of these. First is routing. So there's some sort of algorithms there. The routers, given the graph of the network, computes the shortest route. At the end of it, we generate a routing table like this, a forwarding table like this. And the way we look up this table is by matching the destination address, of the packet. And so if a packet comes into a router, inside the router takes the destination address in the packet and look up this table. If there's a matching entry, the router discover what is the next router to forward to, what is the right direction to pass this packet further. Okay, you see, router oftentimes well connected to other routers on the internet. So this router here could have multiple ways of passing the packets further. Unlike the very simple scenario there, each router has only 1 outgoing link, right? So it's no longer that intuitive why packets need to be stored and then forward. Now you see, packets need to be stored here, and then the router can look up this field and match this entry and then discover, okay, this packet is supposed to go out on network interface 2, this direction, to this router next. Similarly, this router needs to store the packet entirely, and then it can look at the header, this particular field, destination address, and find out in its own routing table which router next to forward the packet. Yeah, it's exactly because of the forwarding functionality that's required to pass data around over a packet switch network like internet. So on packet switch network, we store packet before we forward it. So forwarding here is to move packets to routers all the way from the source, eventually reaching the destination. Right? We'll definitely tell you more as we come to chapter 5. Okay. So in datagram network or in data network, the way it works is let's receive a packet entirely, okay, and look up the destination address to determine which is the next hop. And so you see, if the routing table change, if the graph change, routing table would change. When the routing table change, when the forwarding table change, Yeah, the subsequent packets might be following a slightly different path to the destination. Okay? So the routes packet traverse might change in a session, in a data stream session. So the analogy here is that the packet switch network is a little bit more like the regular car network. Okay, if we are driving a car, a lot of times, hey, to find out the next segment, okay, which road segments we should go on, we might actually stop and pause and ask someone for this destination, for direction, or park to the side and then look up Google Map to find out which is the next segment. Right. And actually, in a packet switch network such as internet, we can potentially emulate a circuit-like behavior that is called virtual circuit network. So instead of looking at the destination field in the packet header, we look at a very special header field called the virtual circuit ID field. Okay, so there's a tag there, carries a number. Okay, that number determines which is the next hop. So inside a packet, there could be many fields in the packet header. One is called destination. There's another one called the virtual circuit ID. And one can look up that field and decide which is the next hop. And how do we do that? We'll talk about that also in chapter 4 and chapter 5. And what's nice about this approach is that we can then try to ensure, okay, all the packets for that stream traverse a fixed path. In a way, packet number 1, 2, 3, 4, chances high that they arrive in order. In this case, in case routes might change, if the later route is shorter than the earlier route, chances there packet 1 might arrive after packet 2. So, packet switch network. To sum everything up, this is general communication network. Two different flavors depending on which philosophy we design the core of the network. If we are going for a circuit core, it's called circuit switch network. If we are going for a packet-centric core, packet switch network. In circuit switch network, we know there are different ways of dividing resources into pieces. Frequency division or time division. But either way, it's very regular following certain order. Things will need to be reserved. There's a call setup delay. It's good for long-lasting calls where you will prefer data not experiencing variation in delay, not experiencing losses. But this is very resource consuming. Each time we will not be able to allow many users going on at the same time. On the other hand, packet switch network, simpler, flexible, no idle resource, but we might have congestion. So that's this track, datagram network. We look to the destination network address and then decide which is the next hop to forward. And so we need to store the entire packet, and so they might get queued. And they might get dropped in case there's not enough space in the queue. But we can also try to emulate a circuit behavior using the virtual circuit tag, which allow us to look up into the packet header field that's a little bit faster and streamline the process more or less and maintain packet arrive orders. Packet switching versus circuit switching. And now you have the complete picture in case you need to build your own computer network, right? Two major camps, right? In circuit switching, there are ways of multiplexing data or division data. Packet switching, of course, you can go the contention way, but you can also try to add mechanisms such that there's less contention for certain traffic. Now, the next topic, network of networks. This is actually not to talk about the mechanisms or design philosophies of a computer network. This is to try to give you a visual sense of how internet is like. Okay? So previously, I've been showing you a small, very concise image of the internet where we have residential network, university network, mobile network. Okay, but no, here, what I'm gonna show you is actually closer to what the internet might look like. Okay, it's a network of networks with some loose hierarchy. Okay, now the next two videos is gonna illustrate the earlier way of forming the hierarchy. Okay, so the traditional way of forming the hierarchy is that the large ISPs sit at the top, okay, and everybody else listen. Okay, but the recent decade, things are gradually changing. Okay, so let's find out. First is a little bit more traditional. Okay, at the beginning of the internet, how people try to connect the subnets together. Internet structure. It's a network of networks. Earlier we learned we have end systems at the edge of the internet. They're connected to the core through the access networks, which are part of these access ISPs. Now, some of these ISPs serve home users more. They're called the residential ISPs. Others serve companies and universities. They are more often being called institutions and ISPs. Well, either way, any two hosts in these ISPs wanting to send packets to each other, their access ISPs will need to be interconnected. As a result, we see a network of access networks. Over time, they grow pretty large and complex. And much of these growth is driven by the economics, and some of it driven by governmental or business policies. In the next few slides, what you'll be seeing is essentially the evolution of the internet. What I'm drawing here is a bunch of these access ISPs, or I call access nets here on this figure. Let me just omit drawing the end systems because there's just going to be too much of them and the picture gets too messy. So the first thing the internet engineers are thinking is this: how are we going to interconnect these guys? Well, one obvious way is, how about connecting them all? But as a result, you see there are n square connections. And when the internet grows, adding one more access net, we'll need to add n extra links. So this is going to be a very expensive thing to maintain. And so internet engineers go with the other extreme. Everyone connects to one global ISP in the middle. So data come here, and the global ISP transits the data for the access net to the destination. Similarly, here. So in a way, the global ISP in the middle here is providing transit services to the access nets, which are the customers. Now, as the internet grows, as the number of these access nets grow, then there'll be more paying for the transit services. Gradually, the global ISP will begin to see profit. And when business is profitable, you see competitors. So now we have not just one global ISP, but multiple global ISPs. So A, B, C here are three global ISPs. They're competitors, but unfortunately, they also need to collaborate. Because what? Just like the access nets needs to be interconnected so that they can serve the end systems, their customers. ISP ABC will also need to interconnect so that they serve their customers, the access nets. All right, so must interconnect. There are two ways for the global ISPs to interconnect. First is to establish peering links among each other. The other is to connect through these IXPs, Internet Exchange Points. Now, these IXPs are special. They're typically set up by government fund or by the nonprofit organizations because it's kind of important that we have these, third company there maintaining the basic operation of the internet to avoid companies, commercial companies, to dominate. So that's pretty much the structure of the internet for a long time. But over time, we see more. So local communities such as this guy and this guy here can also grow. When there's enough number of these access nets around, we begin to see regional ISPs showed up. What these regional ISP is doing is this: offering lower price internet access to the access nets and try to negotiate internet access with the global ISP with a lower price. So hopefully the regional net here finds a margin of profit. So profit here and saving money here. For global ISP, this might not be a bad thing at all because it only needs to deal with one customer, which is the regional ISP, instead of multiple of them. Okay, so less overhead.
Yeah, so you see, to connect a network that big, right? At the beginning, of course, it cannot be a flat network. So there needs to be some hierarchy. So this is very reasonable, logical. But later on, you see that there's a human factor now getting involved because of a business opportunities and competitions. Things are changing a little bit. Now, in the next video, you will see in the recent decade, things are changing drastically because of business, human factor.
And this structure has been there for a long time until about a decade ago. Content provider networks showed up. Let me talk about content provider network by example. So let me use Google here. It'll be easier for you to understand. So Google established these data centers worldwide. Okay. What they do is to go to access networks locally where the data centers are, and then ask to connect to the access network, their data center. Now, the number of machines they are maintaining there at their data center and the connections they are buying from the local ISP are actually comparable to the global ISP here. The entire infrastructure there at the content provider network is just as big as the global ISPs in the middle. But what's a bit odd is this. The content provider networks, they're actually physically at the lower level of the hierarchy. As opposed to the global ISPs, they are at the center of the hierarchy. Scale comparable, but where they are in the hierarchy, very different. All right. In the next picture, let me try to draw the network slightly differently so that you see where they are in terms of how resourceful these provider networks are. You see here then, the most resourceful one at the top, the least resourceful one at the bottom. Okay. So at the center, we have Tier 1 ISP and content provider network. Tier 1 ISP interconnect to each other through peering link, and they also connect to the IXPs. Content provider network somewhat different. They connect to the local access ISPs and IXP. All right. But keep in mind, this is not exactly absolute. Some Tier 1 ISPs might also have access ISPs connections. Google here, if this Tier 1 ISP offers a fair price, might also establish a connection. All right. Good. Now, the final slide is just to give you a rough idea what's inside a Tier 1 ISP. As I'm drawing here, it looks simple, but it's actually quite complicated. This is Sprint's backbone. Sprint is one of the major operators in the US. It's also a Tier 1 ISP.
Each of these red dot is called an is called a POP, point of presence. So the row there is pretty much like a data center in Google. It's a rack of machines. In this case, a rack of routers. Okay, so rack of these routers. They're interconnected between each other, and they are also offering connections to the customers. And some of them might be connected to other tier 1 ISPs. And these links are to go further up into the backbone, in the hierarchy of the backbone in Sprint's network. And this is internet structure, a network of networks. All right, so by now you see that in the core of the internet, there are two major principles to design, right? And you also see how the core looks like. It's not just loosely hierarchical, it's also dynamic, changing. And the role of human factor is growingly large. All right, with that said, we move on to the next section in the chapter. So we'll be talking about how we measure the performance of data transmission. But you see, you guys have already heard about these. When we were talking about packet switching is what? Mix and pass. Mix and pass. And you know what? These issues, okay, troubles we see on the internet are often because of, hey, packets mix before they get passed. So here's a short recap of packet might get dropped, and where packet might experience longer than expected delay, these performance metrics.
Starting from here, we'll focus our discussion mainly on the packet-switched internet. And 1.4 is to talk about the important metrics we care about designing protocols for it. That includes delay, loss, and something called throughput, which we'll talk about at the very end of 1.4. How do loss and delay occur? Well, let me draw your attention to the example below, that'll be easier. First kind of delay is happening here, in the packet that is going out, being transmitted out. That delay the packet is experiencing is called the transmission delay. That is the time it takes to transmit the packet, and we know how to calculate, don't we? It's packet size divided by the link rate. But there's a second kind of delay experienced by packets here before they get to go out. These are what? Packets waiting in a queue, waiting for its turn. And how can there be packets waiting in a queue? It actually happens quite often when the incoming rate exceeds the outgoing rate. So you see in the example, A and B sending packets actively together into the router. In case the aggregated arrival rate is higher than the outgoing rate here, then you will see there will be always packet here waiting to be transmitted, and therefore subsequent packets will need to what? Wait up. And that is queuing delay these packets are experiencing. Now the calculation of queuing delay is a lot more challenging than the transmission delay. It really depends on the arrival pattern before a packet comes into the queue. Okay, now if that pattern is reoccurring, predictable, then it will be easier to calculate this. Otherwise, very challenging. Now, that explains packet delays, where they might occur. Packet might get lost as well at the router, and it happens here. Focus on this thing here. It's the packet queue. The size of the packet queue is limited. Okay. By the way, that packet queue is also often referred to as the buffer. Okay, and the buffer space is limited, just like the memory space is limited. The buffer space is just a way of calling the memory reserved, okay, to store these packets. Now, given that the amount is limited, in case congestion persists for a long time, then eventually you run into the situation. There's no longer free buffer space in the queue. In that case, arriving packets will get dropped, and therefore we see packet losses.
All right, so that was a recap. There's a question right after we talk about how the core of the internet look like, right? It's a loosely hierarchical and dynamic network. So Adri had a question. Social media such as Facebook, do we consider them as content provider network? You know what? Generally speaking, yes. Okay. So inside Facebook, they do have these data centers. They host content, right? But these contents are actually contributed by us, by the users. And we share the content we contribute with other users. But you can see that Facebook behind the scene will be building these data centers, storing these contents worldwide because the users are worldwide. Okay, much like Google, Gmail users worldwide. Okay, so Google hosts their own Gmail content. Google hosts their own YouTube video content. Such as Facebook hosts also our status updates. Twitter hosts all these posts, interactions between the users. Okay, general sense, Facebook, Google, they are all content providers. Okay, but there's also something called content distribution network. It's definitely a content provider. It's the kind of network that companies like Facebook or Google, or if you're starting up a company to compete with Facebook, you might actually purchase services from the content distribution network so they can host content for you. That way you don't need to maintain your own data center. For a startup or for a smaller scale or regional company hosting regional data, that might be a better way to go. Okay, so that is content provider network as well. That is also officially called content distribution network, which we will hear more about in chapter 2. So that's a very interesting kind of business. They kind of build data farms everywhere, data centers everywhere around the world, and accept people subscribing their services. Content distribution network, nowadays there's a sexier name, cloud computing, cloud platforms. If you think cloud services, they are content distribution network. In fact, they are a little bit more than just allowing hosting of contents. They also allow sharing of the computing resources. Okay, so cloud is actually a more general type of content provider or content distribution network. All right, I hope that's clear. But I think it's important to give you guys some more context, okay, so that you can connect all these, brand names you use every day to the entire infrastructure and how we will be referring to these companies, these businesses that you use every day, the rest of the class. Okay, Steven. What about Polly's course website? No, you see, in a very, 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 very general sense, NTU's web hosting services is also a content provider, but it is providing content. But for many people, it's not quite yet at the global scale provider, okay, status. I would say it that way. Okay. By the way, I think some of you might have thought about, hey, how about running a service that I can set up a web server? I know that some of you are very capable of doing that. It's actually not that hard. And PCs these days are quite affordable. So just install Ubuntu and Jinx. Then you can run a web hosting services. And there are plenty of people out there who don't know HTTP, who don't know Unix-based system, who don't know how to operate server. They might subscribe service from you. So then are you a CDN? You are still CDN, it's just that it's a lot smaller scale. All right. Yeah, but in the example that I was showing, right, in order to get at the top hierarchy, Google deserved to be at the top, but Pollys, NTU's web hosting service, NTU as a content provider, then it's definitely still very low in the hierarchy. All right, good. So Stephen, I think that's a good point. That's a good point. Okay, in very general sense, content provider network, of course, okay, if you generate content, and if you are hosting your own content, you are a provider network. But it can be a lot smaller scale, okay, not quite Google. Facebook, I think nowadays quite big. Ever since they start running Meta, I think they kind of expand the whole infrastructure within the company. Yeah, I don't think NTU is really global scale. It's just very local. And you probably observe also that NTU is beginning to outsource the content service to other companies such as Google. That's actually something very interesting to discuss, but it's gonna take too much time. So let me continue with the lecture. So hey, we talk about the metrics we care, okay, so that we can judge which internet service is working better. We can judge whether the network is designed better. And the first metric that everyone cares about is delay. Okay. And the videos I'm going to show you, again, two of them. First is to talk about the theory. And what I'm trying to do here is I speed up the video. I can tell that for some of you, the videos we've been playing earlier might be a little bit slow. Okay, now this, let me try to speed it up and see how you guys feel. So first, theory of delay and how we measure delay. Now, packet delay. There are four components. The first component is the nodal processing delay, but we just call it processing delay. It occurs right here when the packet arrives at the router. Router here checks the bit errors in case there's any, and decides quickly which output link the packet should go out. Next, queuing delay. That's the time the packet waits until it's turn to go out on the output link. So it occurs right here at the buffer space where packet queued up. But the amount of wait depends on the congestion level of the router. Component 3 is the transmission delay, and it's calculated this way: R being the link bandwidth, L being the packet length. And the time to transmit the packet out will be L divided by R. And it's happening right here at the interface between the router and the link. Final component, propagation delay. Provided the length of the physical link and the propagation speed of signals traveling the physical link, we know that the propagation delay is D divided by S. So essentially the time for the packet to traverse the physical link. Be careful, S here is the distance the signal can travel per second. R here is the number of bits the transmitter can push out per second. Although I call S the propagation speed, R the link speed sometime, but there are two very different quantities. Right? Now let's go through a couple examples to exercise calculating transmission delay and propagation delay. What you're seeing here is a caravan of 10 cars. Now the way to think of this scenario is this. Think of cars being bits and caravans being a packet. So we have a packet containing 10 bits in a sense. The cars will be propagating at the speed of 100 kilometers per hour over 100 kilometers, reaching the second booth. Toll booth number 1 here takes 12 seconds to service a car. All right. Question here is asking how long until the packet is lined up before the second router. All right, so transmission speed, transmission delay plus the propagation delay. So what is the transmission delay? We have 12 seconds serving per bit, and then there are 10 bits. So the time to push the entire caravan out of the toll booth is 2 minutes. And then the propagation delay is for the car to travel 100 kilometers. So 100 kilometers dividing the propagation speed. So we have 60 minutes here. And so altogether, 62 minutes before the entire caravan to reach the second toll booth. So you see, in this case, transmission speed very fast, propagation speed slow. In the second example, the configuration is slightly different, mainly propagation speed and transmission speed. Propagation speed now goes really fast, but transmission speed much slower. So question here is asking, will the first car arrive at the second toll booth before all the cars are being serviced? Let's see. When will the first car arrive at the second toll booth? So transmission delay, 1 minute. Propagation delay. So we have 100 kilometer, but we're traveling 1,000 kilometers. So we'll be spending 1/10 of an hour propagating. And that's 6 minutes. Together, 7 minutes. So the first car will spend 7 minutes before arriving at the second toll booth. Now, 7 minutes is also the time to service 7 cars for the first toll booth. That means we have 3 cars that are still behind at the first toll booth. So yes, okay. When the first bit arrives at the next router, there could still be bits not yet transmitted out from the previous router. So in this case, where the propagation speed is really fast, transmission rate very low, you had this weird situation. Good. Let's sum up packet delay. So there are 4 components: processing delay, queuing delay, transmission delay, and propagation delay. Transmission delay, very low, typically microseconds. We just ignore the processing delay when we calculate packet delay. Transmission delay, propagation delay, very easy to calculate. L divided by R, this quantity is often significant and especially the case for low speed links. Propagation delay, slightly harder. It varies quite a bit from microseconds to hundreds of milliseconds. So this extreme is for satellite links, for example. We've seen earlier, it could go up to 200 or even more milliseconds. Sometimes the transatlantic or trans-Pacific links, very long optic fibers, could also take up to 100 milliseconds. Now, in the process of calculating packet delay, the hardest component is this, queuing delay. Now, it's very hard to calculate accurately because it depends on the congestion level at the router. Just to give you a sip of how hard it is, let's define again, R being the link bandwidth, L being the packet size. Let's add one more variable, the average arrival rate. So L multiply A is the average bit arrival rate. That is also the incoming traffic rate. R is the outgoing traffic rate. So we could define traffic intensity being LA divided by R. So when that quantity is close to 0, that means incoming rate very low, outgoing rate very high. Then no bits really need to wait. So queuing delay very small. And it's depicted here. When LA divided by R is very small, queuing delay also very small. The other extreme is here. When the intensity is greater than 1, that means there are more bits coming in than more bits going out. And when time goes on and on and on, the newly arrival bits will need to wait longer and longer and longer. And it's pretty much here, approaching infinity. Now, when the intensity is between very small to 1, delay is simply growing. And as we will be approaching infinity, you see that the curve grows quickly like that, okay, close to an exponential trend. So hard to estimate queuing delay. In fact, it takes a whole semester for a professor to teach about how one calculates queuing delay. And at the graduate school, there's advanced queuing delay that one can also take to make sure that you do a better job, okay, estimating queuing delay for highly dynamic incoming traffic. All right, so queuing delay, ouch, headache. But for the other 3 components in a nodal delay, processing delay, negligible. Propagation and transmission delay, hey, you can compute, okay, depending on the size of the data you want to transmit, the rate of the link, as well as the length of the link, and the speed of propagation, obviously. All right. So second video here is to talk about how we as user of the internet can measure the delay of the data we are sending, okay, or the delay of data that are sent through a particular set of links to a particular destination. Okay, measuring delay.
All right. So that was the theory part of the packet delay. One can also find out what is the real internet packet delay by trying out this program, traceroute. Okay. What it does is to measure delay from a source
one hop at a time, all the way to a destination. So this is what I'm drawing here. Source to destination, and it's sending 3 packets, one at a time, to reach each of the routers along the way. So router there receiving such a packet would return by sending a reply back to the sender. Now the sender there can time the interval between the transmission and receiving the reply and gets one estimation of the round trip time between the sender to the router. So it works like this. 3 probes to the first router, 3 round trip time estimation. 3 probes to the second router, 3 round trip time estimations to the second router. And this goes on and on until it reaches the final destination, and then the trace route program stops. The output of the program looks like this. This is an example. Trace routing from Gaia, umass.edu to Oralcom France. So this is saying first hop router's name is cs-gw at IP address 128.something.something.something. And there are 3 round trip time estimations, 1 and 2 milliseconds respectively. What's a little bit interesting is between hop 7 and 8. There, you see at hop 7, round trip time was about 22 milliseconds, but suddenly to hop 8, the delay is about 100 milliseconds. So that is the transatlantic links connecting from US to Europe. A little bit more interesting is also hop 17 and 18. You see stars, stars, stars. That means the routers are not responding. Okay, and it could be because the probing messages are lost or the replying messages are lost. But it's more likely that the router is turned off replying to these. Routers are on, but the routers turn off replying these probing messages. Well, let's try, sending a trace route ourselves from here. How about that? Let's go over to a terminal and then trace route to say Google. How about that? All right. Good. First hop router. Well, it didn't tell me the name of the router, so chances high that the router doesn't have a name. Okay. Delay reasonable. 10 millisecond, 3 millisecond, and another 3 millisecond. Router 2 here, well, either the probing messages are lost or router turns off the functionality of returning to trace route probes. Now third hop, 30 milliseconds, suddenly much higher. Okay, fifth hop, delay not much higher than the third hop. And you see here, when it's star, 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 it takes longer time. It's because when the traceroute program sends the probing packet, there's a timeout interval. Traceroute will wait until the time exceeds the interval. Then it determines that, hey, the router is probably not going to respond anymore. So forget about the first probe, send the next probe. Next probe waits also some amount of time. Timeout, give up, and then sends the third probe. Okay, good. Finally, we reached www.google.com. But the name is actually quite different. TSA something something. Interesting. And the end-to-end delay, end-to-end round trip delay to www.google.com is about 20 something milliseconds. Now, something that's very odd is here. Hop 8. If you look closer, we do have 3 round trip time estimates, but each time number A here along the way, the 8th hop, is slightly different. IP address is 101, 49, and 97. So you see here, packets, although going to the same destination, coming from the same source, as they go on the internet, the routes could actually change. Also, you see, hey, the time it takes to reach hop 5, 30 milliseconds, but the time it takes to reach hop 12 is only 20 something seconds. So the load of the internet changes also over time. So sometimes when you are probing to a closer router, could take a longer time because it was busier there. But when the traffic load drops and when you're probing a router that are farther away, you could get a shorter round trip delay. Yeah, very curious. And let's go back to the slide. And it turned out that it's a good time to start the next quiz. All right, so it's time for quiz. And I can see from YouTube backend that when it's closer to quiz, number of attendance increase. Right, so this is quiz number 6. Again, let me switch to the whiteboard mode so that I can mark things so you see what I'm talking about. Okay, so the quiz is about traceroute that we just talked about in the video. Okay, and we'll be trace routing to ordercomp.fr. And this is the result of the trace route. Okay, so I'm asking Q1, why the 3 delay measurements we see not quite the same? So you see here, to the first hop, first probe 1 millisecond, but the third probe 2 millisecond. To the second hop, again, hey, not quite the same. If you go down further, 104, 109, 106, not quite the same. Why? Okay, so this is Q1. Q2 asks, okay, look at hop 10 and hop 11 and the 3 measurements. Where is hop 10? Here and here. 10 and 11. Hey, the 3 measurements to hop 10. Right, the delay to hop 10 is what? From the source to hop 10 and back. Okay, round trip to hop 10. Supposedly, right, round trip to hop 11 should be longer. Delay should be longer. But you see, hop 11, the 3 measurements are 112, 114, 112. But the delay, the second delay to hop 10 is higher. Why? Okay. Third, now, okay, what's nice about traceroute is not only that we get to see how long the delay is. You can from the source to a particular router. You can actually do this. For example, can you estimate the delay between hop 3 and 4? So hop 3 here and hop 4 here. So between this. Can you estimate just the delay between router 3 to router 4? But this is from source to router 3 and back. And this is from source to router 4 and back. It's a round trip. And so here I ask just, one-way delay from hop 3 to hop 4. Can you estimate that? And what is your mechanism there? Okay. Similarly, can you extend that mechanism to estimate the delay between hop 8 and hop 9? Where is hop 8? Here. Hop 9 here. All right. So can that mechanism you have designed to estimate the link delay from, to estimate the delay from hop 3 to 4, can you simply apply that here? Okay. If not, maybe you want to change the design a little bit. Okay. All right, so that's Q1, Q2, Q3 for quiz 6. This is not exactly straightforward, but if you pay attention to the videos, at least for Q1 and Q2 and the first part of Q3, it should still be straightforward. Okay. And you know what? It's also time to take a break. So let's take a break while you are thinking, working on it. And after the break, I'll come check on the W3 Quiz 6 channel and see how you guys do. Okay, so the next 10 minutes, the break time, as well as the time you work on Quiz 6. right, so hey, we have one team, okay, managed to come up with solutions. Okay, so team one by Stephen. I see that, yeah, the three delays are very likely different because at the time that probe is sent, the load of the server or the exact route that probe is traveling might be different. So similarly, right, the delay measurements between source to hop 10 versus source to hop 11, it could be that the three probes going to hop 11, for some reason, the server load lower, so the servers along the way, the load somewhat lower, and when the three probes going to hop 10, the server load in between source and hop 10, if some of them are higher, then you could see, okay, the delay to hop 10 and back being higher. Now for Q3, estimate the delay between hop 3 and 4. Yeah, so I see that 3 to 4 millisecond for hop 3 and 4 from team 1. I guess you try to subtract the delay, right? So about 10 milliseconds for the first pair, for about 6 milliseconds for the second pair, and 8 minutes. So divided by 2, you get about 4 milliseconds, 3 to 4. It's a range, okay? That's good. But how did you get 1 millisecond? Sorry, I should edit this. Yeah, so you mentioned that you're taking the differences between the delays to hop 3 and 4 divided by 2. Yeah. But for hops 8 and 6, if you do the same, right, you see, oh, for the first pair, 5 milliseconds being different. For the second pair, hey, it's -7. For the third pair, 2. Did you just add them all up and divide it by 2 as well? Yeah, if you do that, would you think that's a little bit odd? Okay. So are you really estimating the delay between hop, let me see, what was the question? Are you really estimating the delay between hop 8 and 9? Okay, yeah, Stephen, team 1, think about it a little bit more. All right, let's see Ethan, team 11. Yeah, it can be affected by the queuing delay, and the routes can also be a little bit different. Very good. Delay between hop 3 and 4. Yeah, so you take the diff of the 3 measurement pairs and then divide it by... Oh, okay, I see. Okay, this works too. Very interesting. And 8 and 9, 7 plus 2, subtracting 5. Yeah, so you kind of, interesting. I mean, yeah. So I think you see, team 11 is essentially calculating the average, okay, of the 3 pairs and divided by 2. Yeah, so divided by 3 and then divided by 2. But then I think similarly between hop 8 and 9. Yeah, so you have a negative delay. And that's how you get 0.66. Do you think this is going to be very close to the delay between no 8 and 9? The delay between no 8 and 9 should be like a positive value, isn't it? But having a negative here, it's so weird. So let's see. Okay, good. Let's see if other teams think differently, okay, about team 3. I think you guys all get it. Yeah, loading and potential route differences. Because in the demo, in the video, you see that, hey, they could be traveling slightly different routes. Okay, some of the hubs, you see that the routers being assigned in 3 probes are all different. Oh, okay, so team here, team 9. Oh, think otherwise. Yeah, so that mechanism, you take 3 samples, you take the average and divide it by 2, will now work estimating hub A to 9. Yeah, so I think Bing Cheng is simply saying that no, that's not use that method. Okay. Well, we'll see. Maybe there will be another team proposing another way to estimate the delay between hubs 8 and 9. Let's see. Jin Yang. Okay. I think team, let me see, team 10. Oh, okay. So team 10 say, yeah, the data with 3 measurements, it's not going to be sufficient. Yeah. Oh, okay. So this is insufficient. Okay, so we see that there are 2 teams, team 9 and team 10, both say, actually, I'm not sure. Okay, insufficient. Okay, so I guess for the 2 teams, what they would do is probably to take more measurements. Yeah, and team 5 ended up having a negative value for the delay. Yeah, Bingsen here says delay between hub 8 and 9 would be negative 0.666. All right. I mean, hey guys, whether you think it's sufficient or not, and a way that you propose to do the measurement, whether it's really plausible or not, it's one way. Okay, you've got to start from somewhere, right? And then later try to improve it. Good. Roughly negative 1 millisecond, all right. Oh, standard deviation. Okay, so hey, if you apply the mechanism straightforward, it will be negative 1 millisecond. But team 12, I believe. Min Lun was thinking, if I look at the standard deviation, yeah, that set of measurements, that 3 measurements between hub 8 and hub 9 are probably too noisy. It probably doesn't make all that much sense. Okay, good. So in a way, you are trying to be critical to the way you propose to estimate the delay. So for some experiment, for some measurements, it makes sense. For some other measurements, you are not comfortable. So chances high that you probably retake them. Oh, okay, team A here is taking the absolute of the difference. All right. That is one way. That is one way. Okay, so guys think. All right, let's see. Delay. Yeah, in case the path is different, then just subtracting them with absolute or not, it might be a bit risky. Okay, so I see some of the teams are a little bit more conserved. a little bit more reserved, okay, as well. Taking a very simple estimation mechanism. All right, good. Guys, we won't have time, as Polly mentioned back in quiz 5. We won't have the time going over all your solutions. But you see, the point of these quizzes is definitely trying to get you into thinking. Yeah. I think a very important training that you want to, important ability that you want to pick up in college is also critical thinking. That, I think, translated into Chinese is called 独立思考. Critical means that you are never really comfortable, right? You ask why, and you think about whether someone's saying something that really makes sense. That is not like saying that being impolite to someone. No. It's, going for the best solution. You've got to see the weaknesses in something in order to come up with a solution that is better. Okay, so here, exercise your critical thinking, and you can critically treat your own solution estimation method and make it a bit more robust and a little bit hard for others to criticize. All right. So, very good. I see you guys all suddenly have lots of ideas. Very good. And if you feel like editing the solution, some of you find that the 3 measurements we see in quiz 6 slide, no. Then what would you do then doing the measurement? Okay, so you might need to change the way you measure, or you might need to measure more until when? Or you can also do outlier detection. Yeah. Okay, so there could be numerical methods that you can apply to make the estimate more robust. Good. Great job, guys. So I see more teams are typing up. Okay. And you know what? There are actually more questions. Yeah, so I see Ethan editing. Great. Oh, it doesn't show really? Okay. So, hey, you know what? Just maybe post add another post in case you don't see the editing showing. Okay. So that you'll be safe, Ethan. So Mark is asking, I want to better understand what factors impact the delay. Can you suggest any course here, NTU, or any other material? Okay. This is a good question. Good that you want to know more. So there could be queuing courses offering queuing delay, but it's usually at the graduate level. If you search, I think the course selection system, you might see a course called queuing theory. All right. But in this course, you learned about how you estimate queuing delay. And exactly how the queuing delay is going to turn out depends very much the arrival pattern. So these packets coming in, if they arrive at a certain pattern, then the delay estimation could be, the model you apply can be very different. All right, good. So, hey, let's come back to the lecture. Hey, we have 2 other metrics we have not yet talked about. Okay, these are the 2 metrics, packet loss and something that you hear about the first time today. Okay, throughput. Well, let's start with the easier one, packet loss.
Packet loss is a lot more straightforward. You see, it's because the queue is finite in capacity. So in case a packet arrives when the queue there in the router is already full. So you see this full packet here, will need to be dropped. That's why we see packet losses. Now, what we haven't discussed is this, the lost packets. to some application, it's actually okay to have packet losses. If it happened, let it happen. So we will not try to retransmit the packet at all. But in some cases, for some applications, users are expecting the messages arrive fully intact. Then we might need to retransmit. Now, as to which entity in the internet to try to do the retransmission, it's really up to the design. So in some cases, we might see the previous routers doing the retransmission. But in most of the cases, we see the original source, the source end system is doing the retransmission.
All right, now the throughput. Okay, throughput is actually counted in a unit such as how many bits per second, but it's not quite the link transmission rate, because link transmission rate is always suggesting what is the maximum number of bits per second this link is capable of sending. Okay, throughput is actually talking about the maximum bits per second a connection between a pair of sender and receiver can transmit. Okay, it's not link bandwidth. It's actually how effective the sender can push bits through a connection which is composed by many links to the receiver. All right, so throughput.
Throughput is the third metric, and it measures this thing, the rate of transmitting data all the way from the sender to the receiver, from one end to the other end, and the speed of data is going through the entire channel, entire pipeline. Now, there are two ways of quantifying throughput. One is called the instantaneous throughput, the other, average throughput. Now, the units are both bits per second. Okay. But instantaneous throughput is more that you're measuring the throughput at a particular point in time. You will see that if you measure instantaneous throughput, it will fluctuate depending on the situation of the channel between the source and destination. But if you observe over a longer period of time, then you see that the average throughput is more or less stable. Okay, so the throughput here we're talking about and discussed throughout the rest of the sites will be more the steady state behavior, the stable average throughput, just to clarify. Now let me elaborate the example a little bit more. This is the sender, this is the receiver. The sender is essentially a file server hosting big files here. Let's say the file of F bits is being sent over to the client requesting the file. And so we're talking about just the file download, okay, not the request part. And connecting the server and the client, we have one link, one switch, and another link. So it's a two-hop network. And the link capacity for the link directly adjacent to the server is RS, and S here indicates it's the link to the server. And this guy here has the link capacity of RC, and C indicates this is the link rate for the link connecting to the client. Now, let's consider, okay, such a data pipeline as a fluid pipeline, water pipeline. Then you see, I'm drawing, okay, the pipelines with the diameter based on the link capacity, RS. So RC here, let's assume it's larger, then you see a bigger pipe versus RS, smaller pipe. And you can also think about the server here being a what? Okay, a water tank, dumping waters, dumping fluid into the entire pipeline here. Now, it might be a little bit easier for you to imagine, right? What is going to be the pipeline's throughput if you consider how the fluids will be arriving at the receiver effectively? Would it be RC or RS? Well, it's probably not that hard, isn't it? Because the intuition tells you that, hey, this guy here, RS being smaller, will limit the amount of fluid that can travel through. Okay, even though RC is bigger, yeah, the amount of water that will go through here effectively to the receiver is still RS. If it's the other way around, RS being larger than RC, yeah, there could be a lot more water coming in, okay, overall carrying RS throughput, but this guy here being thinner is going to limit the rate of the fluids travel through. So in the end, at the receiver, okay, RC is going to be the throughput. And this guy here and this guy here, the link on the end-to-end path with the smallest bandwidth is going to constrain the eventual throughput. Okay, so throughput here oftentimes is being called the end-to-end throughput to indicate that it's the rate of data being sent from the source, one end, to receiver, the other end. Well, after drawing the data network to a fluid network, you see that it's very intuitive how you derive the throughput from one end to another end. And those scenarios are very straightforward, just two links. Let's consider a case that's a little bit more like the internet, okay? Deriving the throughput for an internet-like scenario. So you see here, we have servers and clients, okay? Data will be going from the servers down to the clients through the backbone, the internet backbone. So for each connection end-to-end, we'll be going through how many links? 1, 2, and 3. So we'll be taking the bottleneck link bandwidth as the throughput. So we'll be trying to get the minimum of the 3 segments. Okay, RC is this guy, RS is this guy, clear. The middle segment, well, if there are 10 links in parallel, then this middle link here, capacity R, will need to be divided by 10, as I'm assuming the 10 connections are fairly sharing the entire capacity. So the throughput to be formulated is this minimum of RCRS and R over 10. In practice, however, okay, nowadays on the internet, usually it's either RS or RC being the bottleneck. You see, this is an end system, this is an end system. We subscribe access to the internet through some ISP. So this, usually the rate is low. Just like this, the application service provider, they are also subscribing to their ISP. This is also low. As opposed to the big R here in the middle of the internet, in the backbone, those are usually large. It's just that nowadays, there are a lot more connections sharing the big R. Okay, most of the time, RC, RS are the bottlenecks. But occasionally, you might also see when network is really congested, R is not quite enough to allow all the connections demanding services.
All right, so that was throughput. It's one of the important metrics as the receiver or sender. Their experience of using the internet is essentially, right? How many bits get through per second? And we're done with the performance metrics. The next section in chapter 1 is not exactly technical, but to explain something. If you recall the first week when Polly was describing the scope of this course, we said that, oh, of course, chapter 1 is an overview of everything. And then chapter 2, application layer protocol. And then transport layer protocol. And then network layer protocol. Okay. And we seem to classify these protocols, which are essentially mechanisms of messages being sent back and forth on the internet. So all these mechanisms are kind of classified into layers. Yeah, so that is just how network engineers talk about these mechanisms on the internet. Okay, it's to try to build a certain vocabulary, okay, to describe a complex system. Okay, so this next video, very short, just to open this section. Okay, not technical at all.
1.5, protocol layers and service models. Well, this is a very special section. There's not much really technical here, and the purpose is essentially to explain more. You'll see later in chapter 2, 3, 4, 5. The chapter's title is called Something Layer, Something Layer, Something Layer. Okay, we kind of talk about all these internet protocols or internet mechanisms by grouping them into layers. So chapter 2, we talk about protocols running in a particular layer. Chapter 3, another set of protocols running in yet another layer, and so on and so forth. So 1.5 here is to give you an idea why we kind of classify protocols into layers and what does each layer do in terms of functionality, making sure that the internet operates seamlessly. Okay, so we call that the service model, the internet's service model, or the architecture of how we organize software running on the internet.
All right. And now, let's review a few terms. Okay.
Now, let's recall all the terms we've referred to since the beginning. Right? We've seen hosts and systems. They're essentially the machines composing the edge of the internet. And then the core of the internet, right? The other one at the center of the internet being a mesh of interconnected routers. And then connecting the edge and the core, we do have these access networks or access links that operates different kinds of physical media running different kinds of modulation mechanisms. Yeah, access network. So these nuts and bolts compose and form the physical infrastructure of the internet. So this is more the hardware side of the internet. But we also talk about that, hey, hardware is not the only thing that makes the internet work magic today. A lot of times we rely on these applications in order to what? To see a page that we are looking information from. Okay, so applications such as World Wide Web email. And these applications, a lot of times, right, it's implemented in a way that there's some part of the application running on one physical entity and then another part running on another physical entity. So if you recall for World Wide Web, there's the client side on the client machine, and then there's the server, the web server running on the web server machine. Okay? And these are client and server side will need to communicate based on a specific rule. Okay? And so those rule forms a protocol. So there's also a protocol for the World Wide Web. Okay? So this is one example of the software on the internet. And there are a lot of these softwares. Okay? An application is just one kind of software, right? So in terms of software, okay, there are a lot more to talk about, a lot more pieces. In fact, the hardware part, and this is a very simplified view, okay, there are also a lot of other hardware pieces as well. Okay. In fact, to talk about a complex system like this, we do have a major question to begin with. Okay. Is there a way, a hope to organize these pieces so that it's a little bit easier to teach or a little bit easier to discuss? Okay, not just between the senior network engineers, but also for the incoming network engineers, and how the senior ones teach the junior ones. Okay.
Yeah, so we do need some sort of structure to handle a complex system, right? And the next two video is first to show you an example so that you see there is indeed the benefit of organizing terms or mechanism in terms of layers. So here's the first video.
Let me try to use an analogy, air travel here, to show you that it's kind of important to have some sort of organization, some sort of architecture, okay, to make sure a complex system will work seamlessly. And you will see also air travel and internet. Okay. Air travel to communicate people, internet to communicate data. They're somewhat similar, and therefore the architecture used by air travel is similar to the architecture used by the internet. Yeah, by architecture here, I meant the service model, the way the service operates. Good. Now, recall your experience traveling through air. First thing you do, purchase the ticket that guarantees you a seat. At the day of travel, you walk up to the counter, you present your passport and the ticket number. They will allow you to check in your bag and give you the boarding pass. With that, you go to the gate and they let you into the plane. And then the pilot will be negotiating with the traffic control of the departure airport and decide which runway and at what time the plane can take off. And then for a long time, you're just sitting in the cabin and try to get some sleep. But the pilot is busy doing this, okay, routing the airplane. Okay, so as the plane crossing border of some air control, communications will go on again and making sure that the planes traveling the air, the space, will not collide to each other. And hopefully everything is fine at the arriving airport. Again, pilot talks to the traffic control and find out the runway and the time to land. When the gate is connected and open, we may now leave the plane. Most of us go to the baggage claim to pick up our bag and exit the airport. So it looks like it's a series of steps. Very simple. But if you think about it a little bit more, right? Purchasing the ticket is important so that it guarantees you a ticket. So that when you go to the counter, when you're trying to check in your bag, they recognize you, right? And the base of the recognition is on the ticket number, okay? Acquired here and checked here. And in return, you get a bag number, which is used again here. You get also what, a C number, which is used again here. So there are still some communication that needs to be done, for example, between the steps, in between these two steps. Okay? So this component here, more closely related to this component. This component here is also more closely related to this component. And this component also connected and related to this component, even though this is at the departure airport, and this is at the arrival airport. Okay. So you see that there are components that are related, and there are some base in order to communicate between the staff members here and the staff members here. Okay, the mechanism here and the mechanism here. But you see also, for example, baggage check here. Well, it has less to do with the pilot communicating with the central control. Okay, you see also a little bit, right? This is a little bit more like the internet core. The functionality is quite different. But these are a little bit more like the edge of the internet, where you're trying to track data. Here we're trying to track passengers and the belonging of the passengers. Okay. And so that it's probably not that hard to see. There's a architecture there, okay, and it's kind of laid out in layers like this, right? This is communication to traffic control, but at the end. Communication to air travel on the other end. Communication of air travel, but from region to region to region to another region's traffic control office. Okay. So to regional office, it's just to make sure that the height and the orientation of the travel is correct. Now these involves also runway. So you see there's slight differences between these two layers. Now these three, okay, are more handling the passengers and baggages, not handling the plane per se. Okay, so which gate we get in and which gate we're coming out. So your families and members will know where to go to pick you up, for example, to welcome you back, for example. And baggage here, the number is important. At the destination, you also want to know which station is for the baggage claim. There are usually multiple of them, right? So it's also based on the plane number, the flight number. Similarly, ticketing. Sometimes you need to delay travel, right? So you need to call the ticket office again to try to change the date or change the class, okay? And the reference is always, for example, the ticket number. So for communication, you need certain important IDs, important information there, okay, to communicate within a layer. Okay, the claim ticket there for the bag is so that you can pick things up on the other end. But there are also certain numbers. For example, ticket number connects to a bag number. Ticket number also connect to a C number here. Okay, so certain pieces of information might be added there, either to allow communication within the same layer from local side to remote side, or information to allow components across layers on one side to try to relate to each other. Okay, so you see, air travel, okay, is a complex system. If any step goes wrong, it could end up being a disaster. Okay, needs to be well structured to make sure also that it's efficient. So there are layers. Each layer implements a particular function, okay, a particular subservice, okay. And so there will be some internal actions, but they will also depend on services or functions provided by the neighboring layers, okay, from the layers below, okay, or they might also need to provide supports to layers above.
So see, in air travel, a very complex system. Right? If you build some structure to it, it would make sure that the whole system will operate smoother, okay, than having no structure at all. Okay, so the next video is to try to associate air travel, okay, being layered or modular, it actually helps maintaining and rolling a complex system forward.
Hopefully with the air travel example you see, in large complex systems where we have lots of these pieces, it's really good to have some explicit structure so that it's a little bit easier to identify in case there's a bug, which piece the bug is, and to find out what are the related pieces might be partly to blame as well. So having explicit structure, really good. And you see in the air travel example, we have this layered architecture, layered service model. That's exactly what we're using, okay, to manage, to organize internet's operation. And we call that layered service model also the reference model, because we are referring to these pieces on the internet in layers as well. Okay, so it's our reference model for discussion among the network engineers, okay, which you are becoming one as well. All right. So this way of trying to break a large complex systems into pieces, okay, and to define, okay, the functionality of each piece is also called the modularization. All right. So after defining the functionality of each pieces, after finding out the relationship between the pieces, okay, we implement the individual modules functionality. We also implement the interfaces to communicate from module to module. Okay, so that is called modularization. Okay, this is really common. We see in large software systems. Okay, because it's a lot easier to maintain. It's a lot easier to debug problems. And it's also a lot easier to improve the system, to move a complex system forward. Okay, because you see, the important functionalities are well modularized. So if we need to change the way we implement the functionality, we can just change it. Okay, and that change does not need to propagate through the entire system across the different modules. Okay, so a change, okay, in a layers service, a change within a piece, a change within a module, okay, can be transparent to the other modules, okay, because the APIs are already well defined. There's minimum communications required. All right, so it's just like this. Here's an example. If we change the gating procedure and we decided that we let the first class passengers to go last, hey, it's not going to change how the pilots communicate with the traffic control, right, in order to find out which runway to take off. So each module more or less independent, and the communication across modules, across layers are minimal. Modularization, or layered reference model, layered service model. Sounds nice. Can you think of anything that suggests such a layering is not exactly good?
All right, so that question about whether layering is really good, can it be harmful? That is a little bit challenging. If you know, do tell Polly, type it up at Ask Us Anything. All right, so last video today. Now you see why internet also do the layering, because it's modularized, easier to maintain, easier to communicate, and easier to make changes within a layer, within a module. All right, so here's finally the IP protocols in layers.
Here's the internet protocol stack, and you see here what I'm illustrating. It's in the layered architecture. The layer at the top is the application layer. So these protocols at the application layers are, okay, literally to support the applications. For example, HTTP is supporting the web application. So you do have application processes sitting on the web browser side and another application layer process at the web server side. Okay, and there's a protocol there. For example, a message go out is necessary from the client to request for a web page, right? And that web page will be another message coming back the other way. Well, that's pretty much what HTTP defines, right? So these messages to control when to start sending and which web pages to send. Transport layer, that's one layer down. Okay, the functionality is essentially to allow these application layer protocols to specify, okay, whether these data that I'll be sending through, these data packets I'll be sending through the internet is going to be reliably transferred or best effort transferred. Okay, so this is to administer data transfer from client to server process or vice versa. Network layer protocols, on the other hand, very special. Yeah, all these packets, oh, by the way, packets, when it arrive at the network layer, it's called another name, datagram. So these packets coming from the source, right, needs to find a way to the destination. You see, at the core of the internet, we do have a mesh of interconnected routers, don't we? A router could have multiple connections to other routers. So each router will need to know, okay, which is the right router to forward next so that the packet will arrive at the destination with the shortest distance possible, right? Because you do want the packets to arrive at the destination as soon as possible. So a good routing protocol is to ensure something like this. So network layer, the protocols there are essentially to handle packets being forwarded and the directions of how these packets being forwarded in the core. Link layer protocol. Okay, so these are very special. They work a little bit like, honestly speaking, the transport layer protocols. Okay, transport layer is to handle data transfer from one process to another. Link layer protocol here also handle data transfer, but it's between one network element to another one network element, one network hardware to another network hardware, or a network entity to another. For example, between two routers directly adjacent to each other, there's just one link. Okay, so this might across several hops at the transport layer, but link layer protocol only handles data transfer in one hop. Okay, so it deals with the data transfer very locally within a link. For example, Ethernet is a link layer technology, a link layer protocol.
All right. So that's all the time we have. There's one more video about how the packets traveling through the layers within a node and through the network, through another node and up the layers and down the layers. That I nicknamed a day of life in a internet packet. But that video is a little bit long, about 6 minutes. So we're gonna show that next week, okay? And after that, we'll start chapter 2. Okay, so by the way, there's a section in chapter 1 that talks about internet security issues. We won't have time to cover that during the lectures, but the videos, okay, the unit videos are there available on the Google channel, the YouTube channel. All right, so with that said, that's all for this week. Okay, go get lunch and enjoy the rest of the week. Now, there are a couple more minutes left in case you have other questions you want to ask. Feel free to post. And Polly is going to stay on the channel for a little bit longer. Okay. And the next hour is office hour. So in case you want to just, talk and speak, feel free to call in. All right? And now, officially, goodbye. Alrighty, bye. Wake up.